Hello and welcome to the web series, ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
Okay, hi everyone. My name is Emma. I'm a postdoctoral researcher at the Norwegian Institute for Water Research here in Oslo, Norway. And I'm working on the ZeroPM project using passive samplers of PM substances. So that's what I'll be talking to you about today. Okay, so I'm part of Work Package 7, Technical Solutions, where the objective is to demonstrate how and if legacy prioritized PM substance pollution can be remediated. And part of my project here is looking at monitoring those emissions from the treatment technologies developed by our partners on ZeroPM using passive sampling. So what is passive sampling? So passive sampling is usually like a device where we can measure the concentration of a contaminant in the dissolved or labile phase in water, but also could be sediments or soil pore waters and air. And it's based on diffusive processes. This can be in situ on site or ex situ in the lab, and it's the bioaccessible part or fraction of the medium that we're looking at. Usually you would deploy your samplers over a period of days to weeks to months, and we can get improved limits of detection and simplified sample matrix using passive sampling compared to traditional grab or water sampling. And this can look like, many different passive sampling devices for many different chemicals of interest, and again, in many different matrices. So we have 4 different ones that I've displayed here. So the polar organic chemical integrative sampler is a sorbent that is sandwiched between 2 membranes and then sandwiched between 2 metal rings. Then the microporous polyethylene tube is a sorbent-filled microporous polyethylene tube capped at the end. And then the DGT is the diffusive gradient in thin films, which has a membrane of usually polyether sulfone membrane. And underneath that is a hydrogel or agarose gel layer, and under that is your agarose gel embedded with your sorbent or receiving phase. And then we also have the gradient time integrative passive sampler, which is the GTIP, which uses water as the receiving phase with a membrane of nylon. And I think the important part here is they all have different surface areas, they all have different applications, but they all have a receiving phase with a membrane. And that receiving phase, we can change the different sorbents to match the chemicals that we're interested in looking at. So the operation of the sampler is we'll pick which sample if we want based on what we need, deploy it into our environment, whether that's groundwater, sea, surface water, treatment plants, expose for days, weeks, months, and then we get the sampler back, which it often doesn't look the same as when we deployed it. The samplers then will be extracted and analyzed, and then we'll model the mass accumulated to calculate back concentration that was in the water at the time of sampling. And mechanistically, this looks like, not looks like, but this is the mass transfer coefficient model. So we're looking at an additive model of resistance to mass transfer. So KO is the mass transfer coefficient, usually in meters per second. And it is, I'm not sure if you can see my mouse or not, but it is additive resistance of your water boundary layer, so your chemical to go through your water boundary layer, to go through your membrane, and then to go through your sorbent. And your sampling rate is proportional to the mass transfer coefficient. And your sampling rate is usually milliliters per day and related to the surface area of the sampler. And I'll get into a little bit more about this as we keep going through the slides. So in terms of passive sampler development, which is what we're doing as part of ZeroPM, we need to look at the membrane, how well it acts as a, how long it takes for your chemicals to get through that membrane, the affinity and capacity of your sorbent. Then we need to calibrate the device so that we can get some sampling rates and see if the sampling rates remain in that linear phase of uptake. And then once we've calibrated, we can use it to do the monitoring, which we have done a little bit of. So in terms of membrane transfer, what we did was a diffusion cell with a stainless steel mesh. And we've done that diffusion cell experiment. We've done affinity and capacity. So we've looked at the HLB discs that we're interested in. And then we're showing a bit more of the calibration and the monitoring today. So what is a passive sampler calibration? So the objective here is to understand the process of uptake of chemicals into the samplers, usually under controlled conditions. So ideally in the lab where we can control for flow rate, temperature, and analyte concentration. And from this, we can determine a sampling rate, which is your volume of water extracted by the sampler over time, so milliliters per day or liters per day. And we can calculate the maximum sampling rate. So your RS max is the maximum sampling rate for the sampler design. And this becomes quite important when we look at environmental conditions. So environmental conditions can affect the uptake, and this includes your turbulence or flow conditions. And these flow conditions are often not reported in calibrations, making it very hard to use or compare sampling rates or to replicate those conditions easily. And this is important because when we look at the mass transfer coefficient, that water boundary layer, or KW, is important for calculating RS in situ. And RS in situ is your sampling rate in the field, so then we can calculate back our concentration in the water in the field. So your RS max is ideally close to your RS in situ in the calibration, where we have maximum efficiency, but it isn't always. Plus our area of our surface, the surface area of our sampler, times by this water boundary layer. So we need to estimate the water boundary layer, or KW, to estimate RS max, especially when we deploy in uncontrolled conditions, so environmental conditions. And in the field, KW naturally varies with water turbulences, so this can be estimated by using alabaster plates, which are usually a calcium carbonate or a calcium sulfate that then dissolves over time with the flow or the turbulences in the water. Or we could use performance reference compound spiked silicon, where the PRCs will dissipate at a rate that can help us measure KW in the test system as well. So we set up a calibration for ZeroPM using the one-sided POCES sampler. We used a 5 micrometer pore stainless steel mesh membrane and 2 different configurations or receiving phases. So one HLB-A, which was 90% sorbent and 10% binder, and HLB-B, which is loose sorbent inside a glass fiber membrane. We put all the samplers into water that was spiked with roughly 50 nanograms per liter of PM substances and removed those samplers at days 1, 2, 4, 7, 14, and 28 days. And we also added the PRC spiked silicons into the test system. And here's a little display of the calibration in process. So as it was going, you can see the samplers all attached at different depths and spinning around in the water. So our water concentrations, ideally, we wanted to keep fairly constant throughout this experiment. Our initial spike was around 80 nanograms per liter. And in the figure, what we see is an average concentration in the water of all analytes that was measured, plus or minus 20% of that value. And as you can see, we couldn't keep it exactly plus or minus 20%. And that's because when you take a sample, you have to extract it, you have to analyze it, and then process that data. And then so it takes a while to get it. There's a delay in that process. So the concentrations varied a bit. And then we had to replenish at days 4 and 16 to keep the concentrations roughly in that plus or minus 20%. And this is important because when we look at modeling of the results, the models are not straight lines as we might have hoped. So what we see here is the accumulation model, so the nanograms accumulated in the samplers over time. And in HLB-A and for HLB-B, we've got benzotriazole as an example and perfluorooctanoic acid, or PFOA, as an example. And the black dots are the mass accumulated at different times in the passive samplers. The gray line is a linear model that we've calculated, and then the black line is a nonlinear or a curvilinear model. And what we see is that HLB-A, the nonlinear accumulation, shows that it was reaching equilibrium. So the samples are reaching equilibrium with the concentration in the water by day 28. Whereas HLB-B, the linear model, described best the accumulation in the sampler. And this is reflected in the calculated sampling rates, or the RS, where HLB-A had much higher sampling rates than HLB-B. And this is primarily because we have HLB-A, which is 90% solvent and 10% binder. Then it has the stainless steel membrane, whereas HLB-B has the loose solvent with the glass fiber membrane and then another membrane, which adds another layer of resistance, meaning that the influence of the water boundary layer is less. So this means that HLB-A is more sensitive to water turbulences than HLB-B, which means HLB-A, we always need to use these PRC silicons for estimating that water boundary layer, whereas we don't need to do this for HLB-B because the RS max is already lower, more relative to what we found in the calibration. So in terms of our passive sampler development, we've calibrated 2 different passive samplers. And so now we can go on to the last step, which is monitoring. So we did some field deployments in Germany in summer, and this looked a bit like it was 2 different drinking water treatment plants at Rastatt and 1 at Upper Rhine. We deployed for 3 weeks. We had 3 different types of passive samplers that we deployed, along with the PRC spiked silicons because of what we found in the calibration experiment. And then water was also sampled at the time of deployment and at the time of retrieval. And on the right here, the picture of the bucket shows the setup that we had at each of the treatment steps, where we had a tap going into the bucket, the samplers in the bucket, and then an overflow into a drain. And at Rastatt, we're mainly looking at, this is a schematic of the treatment steps that we measured at Rastatt. Rastatt is historical PFAS contamination in groundwater because of agriculturally applied paper sludge. And so we measured at the inlet and after 3 of the activated carbon filters, where the red stars indicate where we sampled or where we hope to have sampled. And then also at the pilot plant at Rastatt, after consecutive activated carbon filter and ion exchange resin, and then also after an ion exchange resin. And we also measured in some groundwater. And again, this is the bucket system where we can see the POCs inside the bucket, the MPTs in the bucket, and then the DGT at the very bottom, and then the overflow. And then at the Upper Rhine, this was bank filtration into groundwater. We measured the river water, which is what the features are here at retrieval of that sampler. We measured the inlet into the treatment plant, and then the drinking water treatment plant has two trains of treatment, exactly the same. We measured one of those, so ozonation after sand filtration and after activated carbon filter. So at field deployment, we use the RS max that we calculated from the calibration experiment, plus the field data of the area, the surface area of the sampler, times by the water boundary layer that we got from our PRCs. And we calculate RS in situ in the field. And when we plug that into the mass accumulated divided by the RS that we've just calculated times by our 21 days, we get a concentration in the water from the passive sampler. And that's what we see in the figure to the right. We see the concentration in the water in nanograms per liter and at the different treatment steps. And what's really cool is that we see a decrease in the concentrations of the benzotriazoles with further treatment steps, which replicates what we see with the water sampling. So our concentration in the water for the passive sampler is very similar, if not the same, to the concentration measured by water sampling. And the passive samplers are the box bars versus the concentration measured in the water sampling being the circles on the figure. And there is some differences, and this could be because when we take a water sample, we're only capturing a snapshot of that time point versus we know that it can change from day to day, hour to hour, week to week, season to season, whereas your passive sampler is taking an average over quite a perhaps long period of time. But it does lead to slight differences. But for the most part, this is really cool that we are seeing very similar concentrations and that we're still seeing the decrease in concentration in the water with treatment step. We do have more data that we're comparing. So this is just for the POCEs, but we do have the DGT and the NPT data too, which is also looking really promising. So the implications and conclusions are that we have two different types of samplers that we've calibrated. They both operate very differently based on the receiving phase physical properties. We've done a field validation in the drinking water treatment plants where we're able to compare not only the difference between the passive sampling devices that we've got, but also the difference in concentration measured in the water versus concentration measured from using the passive sampling results, and that they correlate really well. And then future-wise, we're also going to look at the POCEs extracts that we have for suspect screening for both phase 1 and phase 2 PM substances. And we may have started to see some interesting compounds already in that. So thank you very much. I've also worked very closely with Ian on this project, so I really want to thank him, as well as Thomas, Donna, Bert, and Malcolm for their help at NIVA, and Marcel and Nicole from TZW, who have been integral in getting the Germany deployments up and running and the water analysis. Yeah, so thank you very much.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.